Hello. In our last episode, we began our discussion on colloids, the special mixtures. Colloids are mixtures that appear homogeneous to the naked eye. They are actually made up of a dispersed phase of single large molecules or clusters of small molecules distributed evenly in a continuous phase, which may be solid, liquid, or gas. What are the different forms of colloids? A solid aerosol is a colloidal dispersion of solid in gas. A sol is a colloidal dispersion of a solid in a liquid. A liquid aerosol is a colloidal dispersion of liquid in gas. An emulsion is a colloidal dispersion of a liquid in another liquid. Foam is a colloidal dispersion of a gas in a liquid. Solid foam is a colloidal dispersion of gas in a solid. Today, we will see how colloids are prepared, purified, and used. Prepare yourself for an interesting half hour of chemistry in action. Meanwhile, let's pause for a short break. Let's prepare a sample of a colloid, ferric or iron 3 hydroxide, from the hydrolysis reaction of ferric chloride. Apply heat to about 200 ml of distilled water until it boils. Remove the source of heat and add 1 milliliter of iron chloride, 1 drop at a time. This method of preparation is called condensation. Here, small ions or molecules clump or coalesce to form particles of colloidal size. Another method of preparing a colloid is by dispersion, whereby big particles are broken down into colloidal size. Galapong is a colloidal dispersion of malagkit, a special rice variety, in water. Used in making many native delicacies, it is prepared by the dispersion method. For centuries, Filipinos have made galapong using a traditional stone mill. During the slow grinding process, the rice grains are broken down into particles of colloidal size. Observe what happens when ferric chloride is made to react with 200 milliliters of 2 molar sodium hydroxide instead of water. Ferric hydroxide precipitates, no colloid forms. This means there is greater attraction between like particles of ferric hydroxide and water molecules. Ferric hydroxide sol belongs to the lyophobic type. A lyophobic colloid is less stable. The dispersed phase has very little or no affinity for the dispersing medium. To what then does ferric hydroxide sol owe its stability? Colloidal particles adsorb ions from the medium. Only one kind of ion is adsorbed, forming a surface that is either negatively or positively charged. A diffuse outer layer of counterions with opposite charge is also formed. Colloidal ferric hydroxide particles adsorb positive hydronium or ferric ions from the medium, thereby acquiring a positive charge. Other colloids like gold and sulfide sols adsorb only negative ions. In the case of ferric hydroxide, the positively charged layer on the surface and a negatively diffused outer layer form an electric double layer. This double layer causes the particles to repel continuously. It prevents them from coalescing for an indefinite period of time. A large amount of negative chloride ions in solution may eventually neutralize the positive charges on ferric hydroxide and cause it to precipitate. To keep the sol stable, we carry out a procedure called dialysis. Place the prepared ferric hydroxide sol in a cellophane bag. Cellophane is a semi-permeable membrane. It allows only the smaller ions and molecules to pass through, but not the colloidal particles. Place the cellophane bag in a water bath. Ions and water molecules diffuse through the cellophane both ways. A white precipitate forms when silver nitrate is added to the wash water. This is proof that negative chloride ions have passed out of the cellophane bag. For more effective dialysis, running water should be used. This will continuously remove negative ions which dialyze out. Dialysis takes place in the kidney, removing toxic metabolites from our blood. These are small enough to pass through the kidney membrane and are excreted through the urine. A person whose kidney is impaired can undergo artificial dialysis. The patient's blood is allowed to pass through a membrane in the dialysis machine. An aqueous solution of potassium, sodium, and chloride ions at the same concentration as that found in the blood flows on the other side of the membrane. We will continue this discussion after a brief pause. What happens if I add an electrolyte like sodium chloride to the ferric hydroxide sole or egg white? The lyophobic ferric hydroxide sole precipitates more easily than the lyophilic egg white. The charge on a colloid can also be neutralized electrically. This U-tube contains a colloidal dispersion of ink. Immerse metal electrodes in each arm of the U-tube. Apply an electrical potential across using a battery. The ink particles migrate to the electrode of opposite charge. This process is called electrophoresis. Electrophoresis is a movement of charged colloidal particles within an electric field toward the electrode of opposite charge. Scientists use electrophoresis to identify protein fractions in a protein mixture such as blood serum. Industries also use electrostatic techniques to paint car bodies and other metal objects. They charge the paint droplets in aerosol spray and give an opposite charge to the metal to be painted. When sprayed, the charged paint is attracted even to the crevices, giving a complete coating. Let's take a look at some interesting phenomena involving lyophilic soles. Gelatin is a common ingredient of many semi-solid desserts. In hot water, gelatin disperses spontaneously to form a sole. On cooling, the protein molecules attract each other, forming a continuous solid network, somewhat like a beehive. Water is strongly attracted to gelatin and is trapped inside it. This structure characterizes a gel. A gel is a special sole that forms only for lyophilic colloids. Some substances, such as seaweed extract, aid in gel formation. They are used as stabilizers in many food emulsions like ice cream and sauces. They increase the thickness of the mixtures. If we leave gelatin dessert outside the refrigerator for some time, the gel will weep. That is, the liquid dispersing medium will ooze out of the network structure. This phenomenon is called syneresis. Syneresis is the exudation of liquid from a gel. The separation of serum from blood, the sweating of butter, or the separation of liquid from meat on heating. These are examples of syneresis. Some gels remain solid only at rest. When agitated, they are liquefied, as in quicksand. This phenomenon is called thixotropy. This phenomenon involves sol-gel transformation. Industries sometimes use paints and printing inks with thixotropic properties. These paints and inks flow only under pressure while being applied onto the surface. The oil drilling industry uses materials with thixotropic properties. Bentonite clay dissolved in an organic solvent like toluene is used as drilling mud for oil wells. The mud lubricates by forming a film between the moving parts. When the drilling stops, it gels and seals the holes of the wells. Protoplasm is the principal material of cells of living things. It is believed to have thixotropic properties. It liquefies when muscles are flexed and gels when muscles are at rest. To make sure that all we have discussed gels, we will sum up the episode after a short break. Today, we learned about two methods of preparing colloids: condensation and dispersion. Condensation is a clumping or coalescing of small ions or molecules to form particles of colloidal size. Dispersion is a breaking down of big particles to colloidal size. We demonstrated a procedure used to purify colloids and thus keep them stable: dialysis. We also observed a process called electrophoresis. The movement of charged colloidal particles within an electric field toward the electrode of opposite charge. We discussed gels or special sols. Gel is a special sol that forms only for lyophilic colloids. Syneresis is the exudation of liquid from a gel. Thixotropy is a phenomenon involving sol-gel transformation. With that, let us leave the topic of solutions and colloids Next time we will talk about energy conservation. This is your host, Roman Miranda, saying good day.